Hey everybody, Chris McClure here. We're going to do a video here without you having to see my face because otherwise the video of my face would cover up some of the graphs that I'm going to show you here. And that's okay. You don't need to see my face every time. So that's okay. You know what I look like. So what we're going to talk about here in section 3.5 involves taking some basic function like the square root function or the square function or absolute value function or whatever, and then transforming it into a more complicated function and seeing what the effect is by these transformations on the graphs. So, for example, replacing x by negative x or adding 2 to x or whatever and seeing what that does to the function. All right, so moving along here. First, we're going to look at doing horizontal or vertical shifts, moving either left or right or up or down. And the first thing that we're going to look at here is what the effect of adding a constant to the function is. So we can illustrate this by looking at the function f of x equals x squared. And then adding 3 to it, x squared plus 3. Now, if you were to draw up a little table of ordered pairs for x squared, this is what you would see. But instead of x squared, suppose we have x squared plus 3. And notice all these numbers are 3 units greater than the numbers for x squared. And then we plot the ordered pairs for both functions. In the black, we have the graph of x squared. In the blue, we have the graph of x squared plus 3. It's just the graph of x squared shifted 3 units up. So look, if you're going to add, say, h units or whatever to the function, then you're just going to shift the graph up that many units. Okay? And same thing if you subtract so many units, like if you have x squared minus 4. Well, the graph of that is going to be the graph of x squared shifted 4 units down. Okay? So you can illustrate that by, again, looking at a table of ordered pairs and then for the x squared and then subtracting 4 from those x squared values. And then plot the two graphs. And again, in the black, you've got the graph of x squared. And in the blue, we've got the graph of x squared minus 4. Again, it's the graph that's shifted 4 units down. Okay? Now, we're going to pull out our graphing calculators. And we're going to plot these three functions. So pull out your graphing calculators. Let's take a look here. And I hope you're following along. So let's go into our equation editor and plug in x squared, enter, and we're going to do x squared plus 2, enter, and finally x squared minus 2. Enter. And let's just go ahead and go to Zoom Standard so we can just quickly do the graph from negative 10 to positive 10 and negative 10 to positive 10 and so forth. So this middle parabola was the graph of x squared. This one up 2 units up, that's the graph of x squared plus 2. This one down here is the graph of x squared minus 2. So you can imagine what x squared plus 5 and x squared minus 10 or whatever looks like. It's just the parabola but shifted so many units up or down depending on how much you're adding or subtracting. So there's the graph of what we just did. All right, moving along here. So here's kind of the conclusion. You add k units to the function f of x, the graph is going to be the graph of f of x shifted k units up. Or k units down if you're subtracting k. Okay, moving along here. Now let's talk about horizontal shifts. We already talked about vertical shifts by adding so many units to the function or subtracting. Now, what if we add or subtract so many units to x within the function? So like, for example, what would the graph of x minus 2 squared look like? Well, compare that to x squared. So here's a table of ordered pairs for x and x squared, and then for x minus 2 squared. And then plot both x squared and x minus 2 squared. In the black, we've got x squared, and in the blue, we've got x minus 2 squared. Notice the graph of x minus 2 squared is the graph of x squared, but shifted 2 units to the right. So when you replace x by x minus 2 in your function, you'll have the same graph, but shifted 2 units to the right. Or if you are replacing x by x plus 2, that's going to shift it 2 units to the left. And this is what it would look like if we were to plug these graphs in the graphing calculator. See the x plus 2 right here? That's this graph right here. It's the graph of x squared shifted 2 units to the left. See, this graph right here is the graph of x minus 3 squared. That's the graph of x squared shifted 3 units to the right. All right, so this just reiterates what we just said. If you replace x by x minus h within the function, then the graph of that new function will be the graph of f of x shifted h units to the right. And same discussion for f of x plus h, except you're shifting h units to the left. So replacing x by x minus h or x plus h, where h is some number, results in a horizontal shift of h units, either right or left. Okay? Moving along here. So if you are looking at the graph of x squared, what would the graph of x plus 4 squared look like? And you'd be right if you said it's the graph of x squared shifted 4 units to the left, like you see for this blue curve. All right, moving along here. Now, what would this function's graph look like? Here we've got a combination of a horizontal graph shift by 3 units to the left and 5 units shifted down when you're subtracting 5. So we'll start off with x squared. That's the blue graph right there. And then we'll shift it to 3 units to the left. And then we'll shift it 5 units down by subtracting the 5. Okay? So you can plot the graph of these more complicated functions by first starting off with a basic function and then doing your various shifts one step at a time. So we started off with x squared, then shifted 3 units to the left. That's the graph of the x plus 3 squared. And then shifted 5 units down, which was the graph of x plus 3 squared minus 5. All right, moving along here. Now let's talk about compressions and stretches. Now, compressions, of course, means that you're kind of squashing it, right? And stretches, of course, means that you pull it away from each other, right? Like you would do with the spring. Now, the first thing we're going to talk about is if you multiply a function by some number greater than 1. Like, for example, multiplying by 2. Let's take a look at the graph of absolute value of x, and then multiply that function by 2 and see what the graph of that looks like. First of all, of course, create a table of ordered pairs for absolute value of x. And here's that table of ordered pair. And then multiply by 2. And you get these numbers. And then plot the two functions. Now, in the black, you got the graph of absolute value of x. In the blue, you've got the 2 times the absolute value of x. And notice that every y value on the graph of absolute value of x when you multiply by 2, you get the blue curve. So in other words, you got to stretch by a factor of 2. This is an example of a vertical stretch by a factor of 2 in this case. And if you were to have 3 times the absolute value of x, then the resulting graph would be even more stretched, this time by a factor of 3 instead of 2. What if you multiply by a number whose magnitude is less than 1/2? Like 1/2 times the absolute value of x. And the result is that the graph of the new function would be compressed vertically. And you can, of course, fill out your table of ordered pairs for both the absolute value of x and also 1/2 times the absolute value of x. And you can plot both the black graph, which is the graph of absolute value of x, and the graph of 1/2 times the absolute value of x. Notice that in the blue graph is just compressed by a factor of 1/2 compared to the absolute value of x. All right, moving along here. So vertical stretches result from multiplying by the function by a number greater than 1. And vertical compressions happen when you multiply the function by some number between 0 and 1. All right, moving along here. Now, we could, if we wanted to, on our graphing calculators, and I would encourage you to do this on your own, is to compare the graph of of the square root of x, the square root of 2x, and the square root of 1/2 x. Now, before we go on to the next screen, what do you think the graph of the square root of 2x is going to look like? And what do you think that the graph of the square root of 1/2 x looks like? Now, notice that for both y sub 2 and y sub 3, that we're not necessarily multiplying the function by a number, we're multiplying x by a number within the function. What effect does that have? And the result is horizontal compression or stretching. It looks like vertical compression or stretching, but really what's happening, first of all, look at the black curve. That's the graph of the square root of x. But when you multiply x by 2 within the function, what that does is it creates a horizontal compression. Imagine taking the square root of x function and taking that graph and compressing it to the left by a factor of 2. And that's what you see here for the graph of y sub 2. And for the graph of square root of x over 2, you're multiplying by a number between 0 and 1, and that result is a horizontal stretch by a factor of 2. Okay? And of course, we could verify that by using the table function on your graphing calculator. I've shown you how to do that a couple times already. And that just kind of verifies the fact that we're not necessarily doing a vertical compression or stretch. It's horizontal compression and stretches. But the relationship between vertical and horizontal is kind of flip-flop for compression and stretching. For the vertical stretch, you're multiplying the function by a number greater than 1, but for the horizontal compression, you're multiplying x by a number greater than 1, and then vice versa for multiplying by a number between 0 and 1 for compression versus stretches. All right, moving along here. So this just recapitulates everything that we talked about here, re-encapsulates, or whatever you want to call it. Just replacing x by some multiple of x is going to either stretch or compress the graph horizontally based on what the value of that multiple is. If A is greater than 1, it'll be a horizontal compression. If A is between 0 and 1, it'll be a horizontal stretch. So play around with all this on your graphing calculator to see what the square root of x looks like compared to the square root of 2x or square root of 3x or square root of 0.2x. All right. So I've got a question for you. Look at the graph here. I'm not going to tell you what this function is, but take a look at the graph. This is the graph of some function called f of x. What would the graph of 2 times f of x look like? Well, you would be right by saying, oh, yes, Mr. McClure, that the resulting graph would be a what? It'll be a vertical stretch, right? And what about f of 3x? Oh, you're multiplying x by a number greater than 1. That means there's going to be a horizontal compression, by a factor of 3. So there's the graph of 2 times f of x. And there's the graph of f of 3x, where you see that horizontal compression by a factor of 3. All right, moving along here. Now let's talk about what happens when you multiply the function by a negative or replacing x by negative x. And the results would be some sort of reflection about some coordinate axis. Now, first of all, if you replace the function by the negative of the function, in other words, just put a big fat negative in front of the function, what effect does that have on the graph of the original function? And the answer is it reflects the graph about the x-axis. And you could see that by coming up with a table of ordered pairs, and for the regular function as well as the negative of the function. And then go ahead and graph those two functions. In the black, we have the graph of y equals x squared. And in the blue, we have the graph of y equals negative x squared. And notice, of course, that y equals negative x squared is the graph of y equals x squared reflected about the x-axis. So the graph of the negative of f of x is going to be the reflection of the graph of f of x about the x-axis. Okay, so that's what we just said right here in this blue yellow box. Okay, now what about replacing x by negative x? Well, the result would be what? This will be a reflection about the y-axis. So this x right here is wrong. This is a reflection about the y-axis. So square root of negative x, that's what you see in blue. Compare that to the graph of square root of x. Okay, so if you replace x by negative x, then the new graph will be the graph of f of x reflected about the y-axis. So let's just kind of go through a quick summary. I know we've covered a lot of transformations, and you're going to need to play with several of these functions on your homework to really master this. But let's just recapitulate all this. Adding k or subtracting k to the function results in a vertical shift, either upward or downward, k units, depending on if you're adding or subtracting, respectively. If you replace x by x plus h, you'll shift the graph h units to the left. If you replace x by x minus h in the function, you'll shift the graph h units to the right. If you multiply the function by some number greater than 1, then you'll have a vertical stretch on the graph. If you replace x by 8 times x, then you'll have a horizontal compression. And if you put a negative in front of the function, the graph will be reflected about the x-axis. If you replace x by negative x, then the graph will be reflected about the y-axis. Okay? So we're almost done here. So here's a follow-up question. Suppose that we've got the graph of y equals absolute value of x. Let's do 3 transformations. The first transformation is we're going to shift left 2 units. What would we need to do to the function to shift the graph to the left 2 units? You would be correct if you replace x by what? X plus 2, right? So replace x by x plus 2, then you'll see the graph in the purple. And then we're going to shift up 3 units. So you'd be right if you add 3 to the function, like you see in the green there. And of course, that's the green graph right there. And then reflect about the y-axis. Now you need to replace what by what? Well, how about replacing x by negative x? When you replace x by negative x, that means that you've reflected the graph about the y-axis, and you'll see the graph that you see in the red, which it really is the reflection of the green graph with respect to the y-axis, the mirror image. So the graph of the absolute value of negative x plus 2 plus 3 is the result of taking the basic function absolute value of x and doing these 3 transformations for the graph. So you don't have to put a whole lot of brain power in graphing this more complicated function, this absolute value of negative x plus 2, and then plus 3. What's going on here? It doesn't know that I'm recording a video. Huh? So now let's take a look at this function here. F of x is equal to 3 over x minus 2 plus 1. How could we graph that? Well, start off with the most basic function that you can, and then through a series of transformations, build this function right here. So we could start off with 1 over x. Very basic function. This is the reciprocal function. There's the graph. And then we could either replace x by x minus 2, or we could multiply by 3, or we could add 1. Your choice. But let's just say that we're going to choose as our next step multiplication by 3. And when we do that, of course, what does that do to the function? All right. Well, you're multiplying the function by 3. So that's going to affect a vertical stretch by a factor of 3. So if you notice this graph right here, which is a graph of 3 over x compared to the original graph of 1 over x, you see that what we've done here in the graph of y equals 3 over x is a vertical stretch by a factor of 3. And then let's replace x by x minus 2. And the result is a shifting of the graph 2 units to the right. And then add 1. And the result is that we've shifted the graph up 1 unit. So through a series of transformations on the original graph, we're able to graph the 3 over x minus 2 plus 1 just by starting off with the basic function 1 over x in its graph and then doing that sequence of transformations. All right, here's, I think, our last problem here. What does the graph of square root of 1 minus x plus 2 look like? So start off with square root of x, and then add 1 to x. Why? Because there's that 1 right there. And yeah, we're going to replace x by negative x. But before we did that, when we replaced x by x plus 1, we shifted the graph of square root of x to the left of 1. And then replacing x by negative x reflects the graph about the y-axis. So if you compare the graph of square root of x plus 1 to the graph of square root of 1 minus x, you see those graphs are mirror images of each other with respect to the y-axis. And then add 2 units. And of course that shifts the graph up 2 units. Okay, so that's it for this block of instruction. You folks have a good day. And by the way, I've posted midterm grades for you. At least in the web info system. Earlier today I was trying to post them on Blackboard. I wasn't having any success because the Blackboard system was kind of spotty. I'll try it again later this evening. And I'll send an email out when I have completed that, okay? So y'all have a good night. Take care, and we'll see you next time.